most people seem to be here. Just to remind you of where we're going with all of this, this is the first slide I put up showing the overview. What we've done so far is we've looked at the big picture and we've looked at some aspects of composition and structure, and we're going to finish off that today and then hopefully pass on to look at a little bit of photochemistry. So we're making good progress through all of this material. By the time we get to the last part of the course after Easter, then we should be able to start looking at some case studies. So, what I was saying in the last lecture, I was talking about composition, and we were looking at something like this, and we were looking at the various different components and how some of them have cycles to do with biogenic and anthropogenic emissions and then chemical processing, and how some of them have no cycle. And what we get in typical atmosphere, clean atmosphere, without any, with constant levels of the various different kinds of emission, is what we get is they call it there a quasi-steady state. What we call it is some sort of an equilibrium. So we have different gases in different parts of the atmosphere, and emissions and sinks and sources and things like that. But generally, it's considered to be in equilibrium unless these things change. However, what we also find is that because of emissions and also because of reactivity, we find that the species present in the atmosphere fall into a range of different reactivity categories. This is one of the most important things that we need to understand for atmospheric chemistry, is we have things which are very reactive, such as OH and NO3 and HO2. These are all radical species, as we shall discuss. Because they're very reactive, they don't move very far from the point at which they're formed. So if we look at either a spatial scale or a temporal scale, we see that these reactive species tend to show fine scale variations. So we can't treat the atmosphere as a big pot with all of the chemical species equally well mixed, because they're not, they show different variations. So fine scale variations in space, so things like this, the concentration of OH varies on a length scale of a couple of meters or so, so it can be radically different, no pun intended, from 1 meter to the next meter in space. But what that also means is, because we've got a spatial scale, we can also think of this in a temporal scale, and these short-lived species show concentration variations on the scale of a few hundred seconds. So these things here, they're mixed with a very fine grid, and they vary quickly in time. At the other end of the scale, we have these long-lived species. These are things like NO2 and methane, but also these various different halogens. And these are not very reactive, with the result that because they're not very reactive, they can travel a long distance, so they show concentration variations on a very large scale. Or another way of putting that is that they don't really show concentration variations over a substantial scale. And what I put at the side here, or what the people who did this diagram put at the side, is some examples of what sort of scales in terms of reference scales with respect to the globe look like. So this is, again, this corresponds to the length scale on the bottom. This is the length scale. So this is what we call the micro scale. Things that vary on this scale up to about 10 kilometers is what we call a local scale phenomenon. Things that vary on a scale of up to 1,000 kilometers, we call those regional or mesoscale, meso meaning midway between things. And things which vary on the 1,000 kilometers to 10,000 kilometers scale, that's on the size, that's the order of the size of the planet. So this is called synoptic or global scale. So some things are going to vary on a micro scale, some things are going to vary over an urban scale, some things are going to show variations but only on a mesoscale, a regional scale, and some things are going to show little or no variation across the whole globe. Relating that to time, and we'll look at the dynamics of the atmosphere in the next couple of slides. So this axis here relates to the time axis on this side. We see we can put in some different values for the sorts of timescales that things happen. So boundary layer mixing time, this is the time it takes for materials formed in the bottom kilometre of the atmosphere, the boundary layer, to mix with the free troposphere a bit further up. So that takes place on the scale of a day, and we'll see why later on. Intra-hemispheric mixing time, this means mixing within the hemisphere. So this is like North American pollution mixing with European pollution within a few thousand kilometres of each other. And what we've also got here is we've got around a year and a half to 2 years is what we call inter-hemispheric mixing time, and that's the sort of time in terms of the gas dynamics, the meteorology of the planet, it takes for molecules to get from the northern hemisphere to the southern hemisphere. So that's the sort of time scale over which long-lived pollutants from, say, Europe mix with those from Australasia. So you can see that if we're going to measure the atmosphere and we're going to quantify the chemistry, we're not just dealing with complexity in a lot of species, we're dealing with lots of different timescales over which those species vary. Okay, so let's just put a few words down on the visualizer for that. So as you can see, with their usual skill and speed, the media services still haven't managed to fix the projector 3 weeks later. I'll be very surprised if it's done before Easter, personally, but we'll see how that goes. Okay, so we're dealing with reactivity and mixing scales. So not only are there a lot of species, but the species vary with different time and spatial scales. So the examples classic there is OH, which is very reactive. As a result of that very reactive, it shows fine scale variation. At the other end of the scale, we've got N2O, which is quite stable. And N2O is quite stable, so it has roughly the same concentration everywhere. It turns out that actually some of these things can be used to our advantage, because these things which are globally mixed to a reasonable concentration, we can use them as what's called tracer species. So if we measure the concentration of some individual reactive species and we measure the concentration of N2O, then we've got we can use the N2O concentration as a reference point. Okay, so long-lived species are used as tracers, that is to say a reference point concentration measurement of the more reactive species. There's a whole science behind how you extrapolate your data. You very rarely see data of just instantaneous concentration shown in some of these big modelling scenarios. usually then model against the tracer and then measure against the tracer, so you have something which takes out variations. It's a bit like normalising things. So what we've got in the middle of that diagram, figure 10, is we've got a whole series of things which have a moderate lifetime and they vary over a number of different length scales. Okay, so the next thing we need to look at, we're going to look at variations. We need to get some physical properties in. We need to get a bit more of a specific handle on the temperature. On variation of temperature and pressure. Okay, so the temperature in the troposphere is largely driven by thermodynamics, and that involves the variation of temperature with altitude, temperature going down with altitude because of what's called adiabatic expansion. Okay. If we start with an air parcel at 0 kilometres, it has some given temperature and pressure. So for example, it might be 298 Kelvin and 1.325 kilopascals, which is sometimes called standard ambient temperature and pressure, you'll recall. Now, thermodynamics tells us that a rising air parcel cools, although it might not seem like it. If you've got a parcel of air and it rises up through the atmosphere, it's got very little way of interacting with the other air around it and exchanging energy. So it's effectively a system where you've got the system and the surroundings in the thermodynamics context are isolated from each other. If they're isolated, that means they can't exchange energy. That's what we call an adiabatic system. So what we've got is, as it rises, it expands. Rising air parcel cools by expansion. If you look at there. Effectively, it's adiabatic, so what happens is we've got the system expands, so it does work. Because there's no ability to change energy from one part of the system to the other on the time scale of the expansion, the internal energy has to drop, so we end up with cooling. So what we end up with is a rate of cooling as a function of altitude. And this is what's known as the lapse rate. The rate of change of temperature with altitude. So this is Z is the altitude, and T obviously is the temperature. You sometimes see lapse rate given the Greek symbol gamma, capital gamma. Okay. Now, we have dry air in the atmosphere, but we also have wet air in the atmosphere. We have places where there's much more water vapour, the relative humidity is higher. And it turns out that dry air and wet air, because you've got different chemical components, they have a different heat capacity, effectively. So because they have a different heat capacity, they cool at different rates as a function of their expansion up in the atmosphere. And you end up with two different lapse rates. we end up with what's called the dry adiabatic lapse rate. It's about 10 Kelvin per kilometre. And for wet air, we have what's called the saturated adiabatic lapse rate, which is about 4 Kelvin per kilometre. So the temperature goes down as we go up the troposphere, and if the whole of the troposphere is dry, it will go down at 10 Kelvin per kilometre as you go up. If there's any areas of saturated air, then it will go down less quickly. So clouds and things like that are regions where there'll be saturated air. But in general, we have a well predictable variation of temperature with altitude. So it looks a bit like this. So the bit we're dealing with here is this bit at the bottom, the troposphere. So we start off with our ground temperature, and the temperature falls approximately linearly depending upon the composition until we get to this region here where we see an inflection. Now, this inflection here is the tropopause. Where the temperature changes sign. So that's one way in which it's defined. There are others, but they're rather more complicated. The simplest way is the tropopause is defined as the point at which the inflection starts to change sign. Okay, so the tropopause is the altitude at which the cooling ceases and the temperature starts to climb again. And the region above that is the stratosphere. And the reason that the temperature has changed is it's no longer driven simply by thermodynamics. This is the point at which the temperature is heated by ozone photochemistry, and we shall deal with this in later lectures. It's dealt with the scheme of ozone chemistry known as the Chapman cycle, and we shall look at that when we look at some gas phase kinetics in the next couple of lectures. So what happens there is that the temperature starts to go up again because all of this photochemistry with ozone, which we'll describe in detail, starts to heat it up again. Okay. So eventually the air density falls to a point at which the ozone chemistry ceases and the temperature starts to go down again. This region is what's called the stratopause. And and above that you've got the mesosphere and the thermosphere and all sorts of other stuff, right? But I'm not going to describe those because most of the chemistry occurs in the troposphere and stratosphere. The variation of pressure with altitude is what we call hydrostatic. The simplest way of thinking about this is, if you remember back to your A-level physics practicals or whatever, those of you who did A-level physics, is if you take a cylinder of fluid then the pressure at different heights through the fluid, we'll start with something at the top. The pressure is high here, and the pressure is low, so the lowest pressure. And this results from the fact that the region down here at the bottom is experiencing the weight due to the action of gravity of all the stuff that's above it on the bottom. So there's pressure from all the weight of the stuff above it. But the atmosphere is a bit like this. So the air acts like a fluid. And because it acts like a fluid, the same physics which governs hydrostatic pressure in liquids also governs the pressure of the atmosphere. And we do another thing that is a bit of a dodgy thing to do, is we assume that the temperature is constant. Of course it's not, but it works well enough for us to be able to use this in a calculational sense. So what we have is we can use the rules from physics that tell us what the height is at some given altitude. So we define this direction here as z. So then we can write the pressure at some given altitude z is equal to, so here's 0, is equal to P0, which is the pressure at the bottom of the cylinder, e to the minus z over this parameter called h, which we'll define. So this is just like an exponential decay. And the term h is what's known as the scale height. And it's given by RT over the average mass multiplied by the acceleration due to gravity. So this is the temperature. This is the average molar mass. Molecules in the atmosphere, and this is the acceleration due to gravity. So you thought you were doing chemistry, I managed to get some physics in, like that. So this is 9.8 meters per second squared. This is 28 atomic mass units, or 28.8 atomic mass units. This is 9.8 meters per second squared-ish. And the temperature typically is around about, we'll say 298 Kelvin. H is about 7.7 kilometers. Okay, so another way of thinking of the scale height is the altitude at which the pressure falls to 1 over E of its value at ground level. So what does this look like? Well, obviously, I've got a graph of that for you, and all the equations as well. You can see that what we've got here is a nice exponential decrease with atmosphere. So the scale height on this chart here, 7.7, right about there. So it's the value at which the pressure has fallen from its atmospheric level down to that over E, 2.71828. So it's fallen to about 30%. So what you can see from this is that the pressure falls quite quickly as we go up in the atmosphere. So by the time we get to 20 kilometres, the pressure in the atmosphere is certainly down to less than a tenth of what it is at the surface. In fact, it's much less than a tenth. So the density of molecules at this part of the atmosphere is going to be quite a lot lower. Now what we can do with this is, because if you remember what I said about number density, we can then turn P of Z using PV equals nRT to give us N over V at a given altitude. So if you remember, N over V at sea level, let's say TP, is 2.46 times 10 to the 19 molecules per cube. Okay, so that's the maximum value. But as you go down as you go up in the atmosphere, that number goes down, and you can use this hydrostatic pressure equation to calculate the number of molecules per cc. Because that brings us back to what we said about mixing ratios. Is the mixing ratio is the proportion of molecules at any given pressure. So the mixing ratio and the absolute pressure gives you the number of molecules, and these things are all interlinked. We shall see a few examples of this as we go through the kinetics part. So when the pressure's fallen to 100th of this value, so for example, if we look at where it's gone to about 100, so about this kilometre, so 100th of that will give us 100th of this number of molecules per cc. Right, that's to visualise it. So P of Z can be used to calculate N over V at any given altitude. Right. The next thing we need to look at is what we call transport. Transport is what all the modelers and the atmospheric dynamics people call it. Wind, it is to you and I. And we generally tend to think of these on two different scales. We have local and regional scale. What we call weather fronts and things like that. That's a local and regional scale sort of transport issue. And then we also have synoptic scale, which is global circulation, which is things like the jet stream and such like that stir things up, but on a much larger scale, and the sorts of things that cause air movement in the tropics and such like. So we've got two different length scales of which these things are happening, but the basic principle is what these things are doing is that they stir up all the chemicals. They stir up the chemicals and particles, so it's partly responsible for, if you take a chemical reaction, the winds will stir it up, but it's also responsible for moving it from one place to another. So they mix up reacting systems. And it transports things to other areas. So the classic example of this would be where you've got pollution in an industrialised belt, and that gets stirred up, so the pollution all gets stirred together and reacts. And then you have these large-scale phenomena moving that pollution across to another continent or out over an ocean or something like that. So we've got two scales of phenomena all interacting at the same time. So air motion is predominantly driven by energy variations. Now what I mean by that is we have different concentrations of energy at different parts of the globe, and that changes things like the pressure, the temperature and the pressure of the gas, and it's that variation in pressure which causes winds to move. So variation in temperature and pressure due to local heating, and that could be local heating of the planet underneath the air mass, or it could be local heating due to the presence of things in an air parcel which absorb energy at some particular position. But predominantly it's to do with heating the air mass. So it's mainly to do with heating the Earth's surface. Then heats parts of the atmosphere. So the classic example of that would be if you've got a piece of ground brown, absorbs lots of radiation, warms up, then it will heat the air directly above it. Hot air rises. Because it rises, the pressure goes down, because it's expanding, and because you've got a low pressure where that pressure's gone down, then air from higher pressure will fill that in. Okay. So hot air rises and reduces the pressure. Cold air, which is at higher pressure, will then fill in, and then you get movement from high pressure to low pressure. Just briefly to go through this, the energy variations are due to differences in the solar variation. So, for example, things like different angles. So if you've got the sun heating directly over the equator, it's hotter over the equator, when you've got the sun heating northern latitudes, it's going through a much larger part of the atmosphere, so the temperature is, the surface heating is much less. So you've got different solar angles. And daily seasonal variations. So for example, what you always see on the coasts is you see the land heats up faster than the ocean, so you get air currents on and off the land in the morning and in the evening. Anybody who does any sailing knows all about that. Also, the energy variations come from difference in reflectivity of the underlying Earth. And absorptivity. I'll just put underlying planet to convey that actually you've got different things that heat at different rates. So you've got different land with different colours. So you've got deserts which reflect quite a lot of light, then you've got brown soil which absorb a lot of radiation. You've got white snowpack which just scatters a lot of light. You've got oceans. Now the oceans have different compositions in different parts of the world, so they have different colours, so they have different reflectivities. So there's actually quite a lot of variation in the reflectivity and the absorptivity of the underlying parts of the planet, and that's partly what drives the complex patterns of weather that we see. Okay, so rotation of the planet also affects the motion of air particles, and we're certainly not going to go into the physics of the Coriolis effect, it's very complicated. But effectively, you have high pressure and low pressure. The air doesn't go just from the high pressure to the low pressure. Because the Earth's rotating, it sort of seems to go in a big spiral, and that's due to the fact that the Earth's rotating. It's a complicated physics effect. We'll jump over that. Coriolis effect. So if you're interested in that, you can go and look that up. I might have to spell it right. Anyway, make it easier to Google. Okay. Now, there are a number of characteristic patterns in the atmosphere, and I'll show you what I mean by this on my next slide. And here's an example of why these patterns occur. Now, one of the sort of most important scale features that mixes things around in the planet are what are known as Hadley cells, Hadley circulation, and this is an example of the equatorial Hadley cell. It's quite easy to follow. So what we've effectively got is we've got sunlight heating the equator. So I'll just... So we have sunlight heating the equator, so we have ground here which is hot, we have warm moist air which then rises. And as the warm moist air rises, it cools. And as it cools, what we find is because there's continuously air rising, it starts to move out and spread out. It doesn't show it on this diagram, but it does this towards the tropopause. And what happens is it spreads and cools out, but it's cooling, and it becomes cooler, and it also becomes drier, because as it rises, we end up with clouds being formed. So these are the things you might see like towering cumulus clouds. You start up with warm, moist air, and it rises up, and the temperature drops, so the temperature then goes below the saturation vapor pressure of water, so the water starts to come out as clouds. And because when you get to the top of the cloud, the water vapor is all gone, you've got cold air and you've got dry air. So that you get cool, dry air circulating down. So this is through the atmosphere. And then when it reaches the surface of the planet, it's cool, dry air, and it's sucked in by the low pressure caused by this rising moist air. So we get a circle going like this, and it's roughly symmetrical around the equator depending on the time of the year. It actually moves to the north and the south as you move from the winter, the summer in the north and southern hemisphere. So we have this Hadley cell which is stirring things round. Now it turns out that there are a number of them at various different positions dictated by the underlying surface of the planet and such like that. So what we end up, because of these, is we end up with vertical air rising, but because the planet's rotating as well, these things then end up showing not just rising up and then condensing down. So you have something coming up here and then going across the surface of the planet and then going down there. Because it's doing that, it appears to travel in a slanted path, and this is why you end up with these swirling patterns of weather, particularly over the equator. So the effect of these things, these Hadley cells and this weather system, is it drives the stirring up of the atmosphere and moves things both vertically and horizontally. Put some words down for that. So for an equatorial Hadley cell, we have warm, moist air driven up over the equator, clouds form, cold, dry air descends, and we end up with a circular stirring motion. And so combined with rotation, it gives us a sequence of characteristic wind patterns. So you end up with the bit in the middle where all the air is coming in, which as you'll see from figure 13, I shan't go back to it, it's called the intertropical convergence zone, because that's where the air is meeting and then rising, and then you get the subtropical high, which is where the cold air is descending, and then further north than that you get a subpolar low, which is the other end of another further up Hadley cell. And this gives us a reasonably predictable pattern of synoptic scale weather. It doesn't tell us much about the local scale. So we're quite close to finishing, but this is one of the reasons why weather forecasting is so much better than it was these days, but still not very good. It's because the synoptic scale and mesoscale phenomena are reasonably easy to follow. The physics of those kinds of things and the maths behind the solution of these things is quite straightforward. It's the fine scale variation to do with local heating and local weather patterns and the first 5 kilometres or so of the atmosphere that's very dynamic. It's very difficult to model. So we know when hurricanes are coming in is a classic example, and you can see where they go up the west coast of the east coast of the United States. But you can't tell exactly where they're going to go because that's subtle variations in the first 2 or 3 kilometres that's almost impossible to predict. So it's the same with chemistry. When we come to model chemistry, we'll see we can predict mesoscale and synoptic scale phenomena reasonably well, but it's the microscale stuff which is very difficult to do because of its graininess, effectively. So just to finish, troposphere is therefore considered what we call well mixed. And the other corollary of this, to do with that inflection in the temperature, is it effectively means the stratosphere and the troposphere are largely disconnected. There is some flow of tropospheric air and stratospheric air. There's some exchange in the polar regions, which we'll look at when we come to look at polar ozone depletion. But by and large, the troposphere and the stratosphere can be considered separately, because there are not very many species that can make the crossover between the stratosphere and the troposphere, or the troposphere and the stratosphere, because the temperature inversion effectively acts like a lid. Okay, we'll stop there for today. I'm sure you've had enough now.